we welcome Dr. Mohammed.
Good morning, ladies and gentlemen. I would like to explain what happened, especially for I would like to thank the organizing committee for inviting me. That happened because of Professor Stephen Seppard had a problem, had a family problem, and suddenly he couldn't present his talk. So they promoted my poster session in order to present it today. So I would like to introduce myself. So Prof.M.Mokhtar, I'm originally from Egypt, working at National Research Center, and then delegated to the Faculty of Science, King Abdulaziz University in Saudi Arabia since 2004. Established a group of surface chemistry experts group since that time, and we have many international cooperation with different universities as well. The topic of my talk today is highly active porous iron phosphate nanotubes, the molybdenum oxide catalyst for the benzylation of benzene. So the outline of my talk today, I will start with the introduction, then talk about the motivation of the work itself, then we'll go to the synthetic mechanism of the material. After that, we explain the catalytic benzylation benzene, presenting some kinetic data, and going to understand what exactly happened, so we can follow by the characterization, synthesis, of the materials itself, and then we'll go to the conclusion and outlook. So, as an introduction, Friedel-Crafts reaction is one of the important organic synthesis materials, and usually the most famous one is the preparation of benzyl benzene or diphenyl methane using acid catalysts. In the literature, the main problem facing such reaction is always this reaction accompanied by more side products, because the product itself is more active than the reactant, so we have more polyalkylated groups formed during the reaction. And the main target is to have a catalyst which is very selective towards the benzyl benzene itself, as well as the other problem facing this one is using homogeneous catalyst during the synthesis of such material, and we have many problems for using the homogeneous catalysts like aluminum chloride, BF3, and so on. That's because of the difficulty of separation, recovery, and disposal of the used catalyst itself, corrosion caused by such materials. So the people start to think for the heterogeneous catalyst instead of the classical homogeneous one. So they think to have acid-solid catalysts. Many trials using heteropoly acids supported in magnesium porous silica, such as M741, 715, as well as support iron-3 and aluminum-3 salts of the phosphoric acid as a catalyst for this reaction. Although they have around very good selectivity, but they still a problem of the leaching effect of the active species during the process itself. So this is the main problem here, how to solve. So we have now to replace the catalyst by acid-solid catalyst, as well as we would like to try the problem of the leaching of that active species. So our motivation, our previous work was using iron-supported zirconia. We get nice results, but still the leaching process is still there. So we started to prepare iron phosphate nanotubes according to the literature, and loading different amount of molybdenum on the surface of the nanotubes itself, doing some treatments in order to have a catalyst which we could expect that have higher reactivity as well as resist the problem of leaching of that species as well. So we go through the synthetic mechanism itself. We started with the iron phosphate precursors, exfoliated by hydrofluoride, adding sodium monosulfate to sulfate, and then co-assembly for the material itself, leaving for a certain time. So at 60 degrees for 12 hours, and then under soft thermal treatment, at 150 degrees. For 24 hours, we put the tubes. Then we start loading, different loading of the molybdenum, starting with 1 mole percent up to 5 mole percent, doing some calcination in order to get the catalyst, different catalysts, and we test these catalysts in the towards the benzylation of benzene. The reaction itself takes place in 3-leg flask batch reactor, which is just liquid phase organic, using the product, injection for the GCMS, following up the product itself, in order to see the percent conversion. Also, we used benzene in excess, using 50 milligrams of the catalyst, and then adding just 1 ml of benzyl chloride in order to the reaction to be first order towards benzyl chloride, and benzene is found in excess. And the product for results, we found that only for the iron phosphate itself, it attained very low conversion, and the conversion increases by increasing the amount of molybdenum loading up to attain 100% conversion after 48 minutes of the reaction itself. This means the reactivity of the conversion increases upon increasing the molybdenum loading on the surface of the catalyst itself. As I mentioned before, the reaction is supposed to be pseudo-ferrous order. We did some kinetic measurements in order to calculate the activation energy and see if it's still related to the amount of molybdenum, understand what exactly happening. The turnover frequency as well as activation energy as shown here from the table itself, that the molybdenum, 5-molybdenum has lowest activation energy as well as highest turnover frequency for this reaction, while FEP, which is iron phosphate, showing highest activation energy with lowest turnover frequency as we mentioned. Now, we would like to understand, so we did the catalyst characterization using first the XRD. So XRD showed only the iron phosphate nanotubes. There is no impurities from molybdenum or any other impurities from iron oxide itself. Only the crystallization increases upon increasing the molybdenum loading, which could be understood in the formation, the possible formation of the Keegan structure on the surface of the catalyst itself. And this is proved by the high resolution term, where these are nanotubes of iron phosphate itself, of an addition of molybdenum. It's like worm-like structure. Then you have here, quite clear, some Keegan structures formed upon loading with 5 molybdenum on the surface of the iron phosphate nanotube itself. In order to further confirmation for the structure of the Keegan structure, we did the third-point EMS NMR. So we could have only one peak here related to iron phosphate. Once you add molybdenum, you have an extra by tweaks here for the NMR, which is showing that the environment itself surrounding, there is a change in the environment surrounding the molybdenum. There is something changing by adding molybdenum on the surface, and this change in the environment could also support the idea of the formation of the Keegan structure, and this increases by increasing the amount of molybdenum added. Further characterization using X-ray fluorescence and deconvolution of the data. So you can see from the Fe to P deconvolution that iron phosphate itself have here number of around 714 electron volt, and 714 electron volt to have for the iron phosphate. Here the molybdenum 714. There is possible different oxidation states, not only or different environments around the oxidation state of iron 3, which is present. But here we can see there is changing by especially at 4 molybdenum as well as at 5 molybdenum and phosphate. Analyzing the molybdenum 3D as well, so we can see there is quite clear in the MO, there is the two peaks appear more clearly at 4 molybdenum iron and 5 molybdenum iron. Confirmed there is quite different environments surrounding the molybdenum, especially higher loadings of 4 and 5 molybdenum mole percent. The rest for the analysis of 1P, this just supporting the POP bonding in the Keegan structure. Further characterization for the surface area and porosity of the material, we could see that iron phosphate itself has high surface area, all mesoporous materials with HS3 hysteresis shape. The surface area, which is 123 meters square per gram, suddenly decreased after increasing the molybdenum at 5. This decrease in the surface area could prove that the formation of the Keegan structure on the surface itself of the nanotube. Further characterization in order to test the reducibility of the catalyst itself, use the TBR, temperature programmed reduction, for testing the reducibility. You can see that iron phosphate itself reduces at high temperature, but after increasing the addition of molybdenum, the reducibility decrease as well as we have many peaks at lower temperature, which means the catalyst now is easily reduced by using the molybdenum, which is also adding to the understand why this catalyst is increases its activity, not only due to the acidic properties of the Keegan structure, but also due to the reducing ability of such catalysts. As a conclusion, you can see that the nano-sized molybdenum iron phosphate composites with different molybdenum molar 1 to 5 was synthesized and characterized towards the benzylation of benzene itself. The molybdenum Fe catalyst showed high activity in the benzylation of benzene, with benzyl chloride with highest activity observed for the 5 molybdenum percent. The most linear increase in the loading was observed, however, it's not the case of the lower loading. It means here we can see that the surface molybdenum mole percent with the bulk molybdenum with the percent conversion, we can see we have highest conversion upon the formation of the Keegan structure itself on the surface. Phosphate mass NMR spectral results indicate the formation of the Keegan structure, and these catalysts are readily recovered. We tested the catalyst many times, tested the regeneration, so it's recovered more than 3 times using biofiltration, washing, using the catalyst itself. But we need further studies in order to confirm the leaching resistance. We tested the liquid itself by ECMS. We didn't find any formation of the iron inside the product, but it needs more work for the filter itself. We need to test the filter itself for this action. At the end of my talk, I would like to thank my student. This is part of the master degree student thesis as my co-supervisor as well, and Gigabyte City for Science and Technology for the supporting of such work, as well as our group for further discussion. And I would like to thank you for your attention.
Thank you very much for this talk. We have time for one question. Yes.
Thank you very much. The P31 NMR results, did you also test the physical mixture of the Keegan ion with the iron phosphate by P31 NMR to see if you get further evidence that you're getting the Keegan ion in there?
No, for the mixture,
Just the physical mixture?
the physical mixture. No, we didn't do so. We can do. nice.
There's another question there, short one.
Yes.
I just wondered if you have also tested the pure heteropolyacid, so without the iron, whether that would also work.
Yeah, if you have heteropolyacid acid already in the literature, there is application of heteropolyacid acid itself.
Okay.
The problem for the heteropolyacid acid itself, as I told you, the leaching of the material itself in the solution. Would like to resist this leaching by supporting on a support to make solid-solid interaction in the material, have stable active species, not dissolved in the liquid during the process.
Okay.
That's what we.
I might have missed that. Thank you.
Thank you very much.